Hi, warm welcome to you. We are going to move forward in the chemical reactions worksheet with single replacement reactions and the net ionic equations for those. So here we'll start by predicting our products. And we will do that on the basis of their ionic charges. So magnesium, for example, magnesium forms a 2+ because it's in group 2. And chloride is Cl-1, which means in this case the iron is Fe3+. All right, so I'm going to replace the iron. We're going to see that magnesium bump off the iron and take its place. So forming a new compound between magnesium and chloride. And that will be aqueous. All chlorides are aqueous unless they're with silver, lead, or mercury. Then what's left is the iron. The iron is going to fall out of solution as the solid, and metals come as single atoms. Iron solid. Let me add a couple spaces in there and erase some of this mess. There we go. Okay, now down in the beakers, I'm going to draw, let's see, how am I going to draw that? Magnesium is like this gray strip. Comes as a solid. And then iron chloride, let me draw my water level here. That is an aqueous solution, so that's going to split into completely individual ions. So we'll have one Fe3+ and Cl-, Cl-, Cl-. Oh, I didn't balance yet. Okay, so maybe we should balance first. Let's see, I've got 2 chlorides there, 3 chlorides there. So I'm going to make those equal by forming 6 chlorides on each side. And then I will fix those up with the magnesium and the iron. Okay, so I encourage you to stop the video and work ahead and then play the video when you have your answers written down. When we look at these initially, and maybe I'll put in, I'm not going to worry about that. Okay. When we look at this initially, magnesium is going to stay solid, right? Magnesium solid. But that aqueous solution, we're going to break that completely into ions. Now in the balanced equation, I forgot my 3. Let me add that 3 in there. I'm going to account for all of the ions. So I have 2 Fe, I'll write this a little more formally. 2 Fe3+, and that is aqueous. And we have 6 chlorides. Yeah, 6 chloride ions. 1- each, and those are also aqueous. So that's what they look like before they react. And I like to line up that arrow, so that looks pretty good. Let's see if I can change that. No, okay. All right. Now what happens on the product side? These that are aqueous also split into ions. So I have 3 magnesium, and now those are aqueous 2+ ions. And that is going to give me 6 chloride ions that are also aqueous. And then we have those 2 iron solid atoms. Excuse me. Okay. So now we're going to identify the spectator ions. Remember, The spectator ions are those ones that don't change. When I look at the magnesium, that looks different. When I look at the iron, that looks different, right? One's floating around in solution and the other one is solid. When I look at the chlorides, though, those are identical. Those are in the same form. So those are going to cancel out, and our net ionic equation is going to look like this for a single replacement. We will have 3 magnesium solid plus 2 iron 3 plus, and those have to be aqueous, going to 3 magnesium 2 plus that are aqueous now, floating around in solution. And you can kind of think of that as being active in the solution. Plus, now those 3 Fe solid, they've plated out. Okay, I made a mistake. That's supposed to be 3 magnesium and 2. Sorry, this should be 3 here and 2 here. Oh, let me cross this out. Okay, not the 2 and not the 3. Okay, right? Yes, 2 iron, 3 magnesium, 3 magnesium. All right, so what does that look like in the beakers in the solution? Now we've got our iron solid down here. And we'll have our 3 magnesium 2 plus in solution and 6 chloride in solution. Now I didn't double these here, but you can see what really has changed. Let me get my little lasso guy. So the magnesium and the iron changed states. They exchanged some electrons in a reduction oxidation exchange to form these here. So the chlorides just sat there watching. These tend to be some of the harder net ionic equations, but it's useful. And we also, you might see later in Chem 161 or 162 that we can split these into half reactions, where the magnesium differ by just the electrons, and then the iron differ by that same number of electrons. So that number of electrons in the exchange has to be equal in order for a redox to work. Okay, we're going to move forward with acid-base neutralization. We see this in 7.4 of your textbook, but I'm going to include some information from 16.1 where they introduce acids and bases. Again, because I think it's easier to work with all the details when you know the foundational ideas. So we've been talking about acids and bases. We actually started out with naming them. And now I want to talk about this definition we've been using. We've been using this functionally because I've been telling you, think of that water as an H together with an OH. And that really helps when we're predicting products and balancing. So we'll think of it in a double replacement reaction where now we've got an H and an OH. So that fits with this definition in chapter 16 of an Arrhenius acid. Those are ones that have that H, they give their H. And then the corresponding base definition is the Arrhenius base produces those OHs. So sodium hydroxide, you see the OH, it just releases those OHs. So that is the Arrhenius definition for our base. So that's really useful for working with chemical equations. So again here, we have that H combining with the OH to form one of our products, and then that X combining with the M to form the other one, the salt metal with the anion. So it's still a double replacement type reaction. The thing that's really unique about it is that now we're going to be forming water in every single case. So that's the hallmark of that acid-base neutralization, forms water and salt. So let's talk for a moment about the definition of acids, where we talked about releasing the H's. So we saw these ones before, and the nitric acid has a nitrate polyatomic ion. Sulfuric acid has a sulfate polyatomic ion. Excuse me. Now the properties of acids were observed to be that they taste sour. They neutralize bases. That's a fundamental definition. They neutralize the base components. They also react with carbonates to decompose them, and they break them down into carbon dioxide gas. They also react with some metals to produce H2 gas. We saw that in the single replacement section. And they tend to turn litmus paper or other vegetable dyes red. So acids turn them red. A base is like the chemical opposite. We're using the definition from Arrhenius that they produce the hydroxide ions in water. And they have different properties. So they tend to taste bitter. So citrus tastes sour with its acid. The bitter flavor comes in like the peel of blueberries or plums is pretty bitter. It's got those alkaloids in there. Alkali is another historical name for base. So alkaloids are basic chemicals, and they taste bitter to protect that sweet fruit in there, to keep the bugs from getting through that bitter peel. Those tend to be like, maybe you've felt a little slippery or gooey. That is also characteristic of basic compounds. They tend to be slippery, they neutralize acids, and they turn vegetable dyes blue. A lot of those alkaloids are toxic as well. All right, so in our balancing, we're going to be using the H from the acid with the OH from the base to form that new water molecule. And notice that this is a pure liquid. We're not going to write water aqueous because water is a solvent, so that would be a pure liquid. We're forming a new molecule of water, which when it's formed, it's a pure liquid. And then on the salt, some of the salts will be solid and some will be aqueous. Okay, so we are going to do these double replacement neutralization reactions. We're going to swap the cations, use the solubility rules. So I recommend that you work through these, write your products, and then continue with the video. And I'll get these all up on screen. So we'll form our water molecule. And then the salt. This is our prototypical salt. It's very simple, simplest equation here. Let's see, we have our H and our OH, so everything's balanced there. All right, moving on. Maybe I'll use those little lines. We're going to combine our H with our OH, and we're going to combine our sulfate with our potassium to form our neutral compounds. Oh, jeez. Okay, there we go. We'll look on the solubility rules, find that all sodiums are aqueous. Now we need to balance. So, oh geez, I did it again. Okay, that's not a sodium. was just looking up above. That is a potassium. So that is K2SO4. So we'll need 2 of these, 2 OHs, 2 H's. That'll give me 2 waters. And the sulfates are balanced, so that should do it. 1, 2, 2, 1 are the coefficients. Feel free to write the charges for forming those new compounds. Phosphate is going to combine with barium. Barium is a group 2 alkali earth metal. So we'll use the crossover method to form the formula of the salt. All right, let's see, we'll need 3 of those. And 2 of those. All right, looks a little weird, but it's okay. We'll use the solubility rules. We get all the way to rule number 7, and we see that this is solid. All right, now we need to balance. The barium helps us out. That gives us 6 hydroxides, so we must need 6 waters, and that will give us 2 phosphoric acid molecules, and that will form this compound here. Okay, next up. Remember that this is a polyatomic ion. This is perchloric acid. So keep that together. All right, we have a ClO4 is the ion, and we will need 3 of those to counterbalance the aluminum. And all perchlorates are aqueous. And that is rule number 2 on the periodic table. All right, now let's balance that. Okay, that should do it. All right, let's do the net ionic equation. This one's a little bit more straightforward than single replacement, right? Because it's a double replacement. We're just going to swap those cations. So again, you feel free to stop the video, work ahead, draw your images, and then check your answers. I think I usually write the salt first, but I don't know. I'm just being consistent writing the water first. You can choose, it doesn't really matter. All right, when we draw these in the beakers down here, that sulfuric acid is going to break into its ions. That's reacting with a base. So I might draw it a little bit differently in a different circumstance. but I'm going to say, okay, let's give 2 H pluses and an SO4 2 minus. In this one, I'll go ahead and use the balanced amounts, Na, OH, and OH. So let's write those out as ions. And those are aqueous, of course. Then from the sodium hydroxide, we'll get those 2 sodium. Plus 2 hydroxides. Great, my arrows are roughly lined up, so that just helps keep a visual. Now those waters stay together. This is a pure liquid, so it doesn't get split up in our equation into the H and the OH because it's a pure liquid, it's going to stay together. And then sodium sulfate, that one is aqueous, so that one does get split up. That's going to generate 2 sodium ions plus a sulfate ion. All right, what spectator ions do we have in solution? The H changes, the sulfates do not change. Those are identical. Sodiums, those are the same on both sides. And then the OHs. So here we get the H plus OH minus goes to water as a new liquid. Now these are aqueous, and they had 2's in front of all of them. So I went ahead and just reduced it to the smallest ratio. So I think there was a question about that in class the other day. All right, I'm going to show this part just a little bit more explicitly. We have these in solution, and those H pluses are going to grab those OHs, and those are going to form that new water as a liquid. Pure liquid formed. And then we still have our Na plus, Cl minus, Cl minus, just bumping around in solution, having a party, spectating. Okay. Moving on, these are a little bit more tricky reactions. These are decomposition reactions that result from a neutralization between an acid and a base, but this time we're looking at the base is that carbonate ion. So that could be sodium bicarbonate, or it could be like marble. If you've seen statues, the acid rain will land on their noses and wear their noses flat. Perhaps you've seen that. We also, if you mix baking soda and vinegar, we see that same thing. That baking soda has carbonate in it. The bicarbonate is going to decompose and form those bubbles. So if we look at this as a double replacement, right? If we were to form the H, and so we're swapping the cations, then that intermediate product, what you would naturally write, is H2CO3 aqueous. That's carbonic acid. Remember, we saw that when we were looking on the solubility rules. It's not on there. If it was with a metal, an ionic compound, that carbonate would be solid, but because it's with hydrogen, it's not an ionic compound, it's an acid, and all acids are aqueous. In fact, this particular one, carbonic acid, as soon as it's generated, it's going to decompose completely into water and CO2. And so that's what we see in the products. We're going to jump immediately right to the water and CO2 in our products. And then whatever is left, those other ions will become the salt. Now, the balancing on these can be kind of tricky because we have different forms. So for example, here we've got a bicarbonate, we've got a hydrogen, so that is still going to go through this process. It looks like it's going to form carbonic acid, but then it decomposes completely. And so we will still have that forming the salt, which makes the balancing a little bit more tricky, but we can still predict those products. So good time to pause the video and write all your products in, do your balancing, and play the video when you get stuck. Leave a little room for coefficients. And now we need to form that salt, and this is a simple one, just sodium chloride, which is always soluble. Oh, and I'm going to add space for balancing. Looks like we do need a little bit of balancing. Now that CO3 loses an oxygen to form the CO2, so there's our oxygen, and we're going to need 2 hydrogens here to make that water. And that's going to form us 2 sodium. So you might start by balancing the sodium. You can start with a metal. That might be a more direct process. And everything else should be balanced. Yep, 1 carbon, 1 carbon. Great. Same products here. Let's just write our H2O liquid, CO2 gas, and then we need to form our salt. That's a calcium nitrate. All nitrates are aqueous. Okay, we've got the calcium is balanced. I've got 2 nitrates, so let's start with a 2 over here. 2 H's and 1 O. Oh, I think that's it. 1 carbon. Good to go. Forming water as a liquid, plus carbon dioxide gas. And this salt is lithium sulfate. And lithium is in group 1 alkali metals, super reactive. It's an active metal. And so that will make it aqueous. Okay, oh, lithium hydrogen. So there's a hydrogen and an oxygen, and hydrogen's here. So let's start with that 2 from the lithium. We have 2 carbons going left to right. Oh, I didn't leave space this time. First time I needed it. 2 carbons, that means 2 oxygens are here. Oh, that's from here. Where's that other oxygen? Let's go into the hydrogens because there's only hydrogen in the water. So I have 2 here and 2 here. So that's going to give me 4 hydrogens or 2 waters on this side. And now let's just check the oxygen. It should come out to be balanced, but let's just check. Oh, and don't include the sulfate oxygen. The sulfate's balanced. We can see 1 sulfate to 1 sulfate. So just look at the other oxygens. So that is a 6 on the reactant side going to 2 plus 4. Okay, good to go. Next one's also a little bit tricky. So we'll start again with our water and CO2. And now our metal is strontium bromide. So those are both simple ions. And we get to rule number 3 for halogens, and we see that strontium is not an exception. So this is aqueous. Okay, we've got our products. We know the formulas. Now we balance. So let's see. The strontium's not helping us. Let's go next to the carbon. Here we have 2 carbons, so we're going to need 2 carbon dioxide. We're going to need 2 bromines. And next, because hydrogen is only in one compound on the product side, let's do our hydrogens next. So for hydrogen, I've got 2 plus, and distribute that 2, equals 2, and there's my coefficient. Oh, and that's the only one. Okay, great. Great. So 2 there. And now let's look at the oxygens. I'm actually going to change color just to make it contrasty. Oh, 6. 6 equals 2 plus 4. Good. Good to go. Okay. So that is a decomposition neutralization. All right, here is our summary page. So if you can get to this point before you take the quiz 5, then you'll be well prepared. This is often a format I'll use. So at the top, we have a lot of balancing, identifying the reaction types, and then down here we have predicting products and balancing. So we'll get some practice. I would suggest that you try to complete this page in about 20 minutes. That's a nice first time through. For example, we'll do this in class. Then I would give you about half as many problems with a 20-minute quiz. Okay, so the way that I'll approach this is I'm going to categorize the reactions first, because sometimes that helps with the balancing or to help see what's going on. And then I'm going to highlight the clues that lead me to where to start on those. So, so let's do it. There we go. All right, 2 aqueous compounds forming a solid. This is a precipitation. Comes by a double replacement. Oh, okay, we took out the double replacement listing. All right, this is a solid with HCl. Oh, forming liquid with HCl. This is a neutralization. Acid-base neutralization. We've got the H plus and the OH minus. This next one is a single reactant in heat. This is going to be a decomposition. This one, let's see, there's oxygen and an arrow. What's going on here? Oh, there's no heat, but I see CO2 and water. This is a combustion, which is B for combustion. All right, and then this one has an ionic compound with a metal. So this is a single replacement. All right, 2 nitrates to 1 nitrate. Oh, yeah, the metals are going to help us here. 1 phosphate to 2 phosphates. So yeah, that looks pretty good. You know what I do on this one? I see it now. This one forms KNO3 as a 1-to-1 relationship from 3 potassium and 2 nitrogen. So I would lead this one off with a 6. Then that is going to give me naturally a 2 and a 3 here. And that's balanced. You could start with the magnesium. That'll get you into it as well. All right, and then I'm going to stick my 1 in just because on WAMAP, if you put the 1s in, then it will grade automatically. Okay, what's going on in here? Again, for this one, this is an acid base, so I see 3 hydroxides and 1 hydrogen to form that one-to-one relationship. So here I might start off with, I've got to form 3 of these. It's going to require 3 of those, and that takes care of that chloride. Oh, and then the rest are 1s. Alrighty. Decomposition. So the tricky part here is to distribute. So I'm going to start with my aluminum here. And then I'm going to go to carbon. I have 3 times 2 is 6. Oh, but I've got 3 here. So I'm going to put 3 here. All right, I'm going to be a little bit explicit because these can be tricky. So 2 times 3, I have 6 hydrogens on the reactant side. And oh, it's just in the water, so that's 2. So I'm going to multiply that by 3. And then oxygens are last. Three times 3 is 9 times 2 is 18 equals, I've got 6 from carbon dioxide, 3 from water, and 9 from our aluminum carbonate salt. Okay, good. Good to go. Right? 9 and 9 is 18. Now next up, start with the carbons. Next we'll do our hydrogens. Look, it's 5 plus 1. So this is an alcohol. This is ethanol. So 6, we'll need a 3 there. And now with our oxygens, we have 1 plus 2x equals 4 plus 3. So 2x equals 6 and x equals 3. Oh, that's not a 3. There we go. Next up, oh, I see those nitrates have that mismatch. The metals didn't help us in this case. So that's one reason I like to look for that. So I'm going to need 2 and 3 to make 6 nitrates equals 6 nitrates, and then the metals fall out from there. 3 and 2. Great. Moving to predicting products. I'm not going to give you any no reaction products. All right, so you got to recognize stuff. What is this first thing? What is this? That is the acetate ion. I like to write it CH3COO minus acetate, which is the anion of acetic acid, which is our active ingredient in vinegar. So useful to know. We're going to see this a lot. Okay. So you see that H, you see that OH. This is going to form, I know it's going to be 2 water molecules plus, and I'll leave space for my salt. I've got barium, and that is going to have 2 acetate ions. Okay, all acetates are aqueous. That is in rule number 2 on the periodic table. All right, let's see, 1 barium, 1 barium. I'm going to need a 2 in front over here. 2 acetates, 2 hydrogens, 2 hydroxides, so that one's done. All right, single replacement. Will magnesium bump off that hydrogen? Yes, it will. It's more active. This is listed first on the activity series. And so we're going to form magnesium nitrate. That's going to require 2 nitrates. All nitrates are aqueous. And then what's our other thing? Oh, what does hydrogen look like as an element? This is going to be the elemental form. This is H2 gas, diatomic gas. All right, so we'll need 2 of those hydrogens, and that takes care of the 2 nitrates. What is this? That's methane. It's a hydrocarbon fuel with oxygen and heat. So this is going to form CO2 gas plus water gas. Start with our carbons. We got a 1-to-1, then go to the hydrogens. We'll need a 2 in front. Oxygens, 2x equals 2 plus 2. All right, so we just need 2 in front. I do recommend that you jot down your oxygen balance in these, just because it's very easy to make a mistake. Just those 2s and 1s. So I go ahead and write those down each time. Okay, what is this? Oh, this has a carbonate and an acid, nitric acid with sodium bicarbonate. So it's going to decompose. Or if you did your double replacement, you might got carbonic acid. That's going to go completely to water. Plus that CO2 bubbles out, maybe the volcano reaction if you did that demonstration or saw that in grade school. And then our salt is sodium nitrate, which is aqueous. Okay. 1 carbon, 1 carbon, so that's good. Now we've just got to figure out our hydrogens and oxygens. So let's do the hydrogens. 2 here and 2 here. Oh, yeah. 2 hydrogens and 1 oxygen. These are all 1s, right? Did you get that? Those should all be 1s. All right, and the last one, will sodium react with water? It is underlined in our activity series. There it is. It is underlined. So yes, it will form a strong base. It's going to form a hydroxide, NaOH, that's aqueous, and that is going to leave us with, what happens to that hydrogen? H2 gas. Right, it's going to bubble off. Forms a metal hydroxide plus the elemental form of whatever that cation is that got bumped off. And so let's see, we're gonna need, we've got 3 hydrogens over here and only 2s here, so we have to increment that up. Instead of 1, we'll have 2 there. So now we have 4 hydrogens equals, we must need a 2 in front here. And that's gonna require 2 sodium atoms. Okay, good to go. So that will be the end of our Friday lecture or class period online segment. And then moving on for Monday, I'm just going to keep on going, get it all done at once. So let's talk about electrolytes and conductivity. And this happens in 3 different sections of the chapters. So it happens when we talk about ions, forming ions, and the fact that ionic compounds conduct if they're molten or dissolved. And then we see it again in reactions where they're talking about, well, look, we formed these ions so they can pass electricity. And in fact, that's a really handy way to measure how much charge is dissolved in solution. And it's not a net charge, it's just a separation of charge that allows electrons to flow from one of these electrodes to the other. So it's the liquid there that is conducting to close the circuit and light the light bulb. So we have this fundamental question, how brightly does the light bulb light up? So this relates directly to ionic compounds and our strong and weak acids, because we can take an acidic solution and test with this kind of a setup, how strong is that acid? How much flow of electrons is allowed by the separation of charge. If you have just neutral molecules, then the electricity can't flow. So this is a really useful segment I want to take some time with to build intuition about what it means, like what's really going on in that beaker, and how do we know that? How do we test it directly? So what's actually present? When we take our sodium chloride solid, we put it in water and it dissolves. Now water's on the arrow here because it's not shown in the reaction. In this case, it's part of the reaction, but the AQ tells me it's dissolved in water. So I know there's water there. I'm just not showing it as part of the balanced reaction. So with sodium chloride, we see it forms 2 ions. If we have ammonium phosphate, though, that phosphate has a +3 charge, so that requires 3 ammonium ions to counterbalance it, which means when sodium phosphate dissolves, which it does dissolve, rule number 1, ammonium is always soluble, we get 4 ions. So we will expect ammonium phosphate solution to conduct a little bit more strongly, burn that light bulb brighter than the sodium chloride. Although sodium chloride does dissolve, does conduct electricity. Okay, this applies for acids as well, because this time it's just that H plus carrying the charge. And we will see it written as H plus aqueous or hydronium ion. And the difference again is just, did we show the water molecule or did we leave it implied by the AQ? Okay, so they're functionally equivalent. The main way they differ is that when you balance your equation, you have to show the same things on both sides. Okay, how does it actually exist? It's hydronium ion, to be more specific, to be more accurate. Okay, so a strong electrolyte has the light bulb glowing brightly. A weak electrolyte passes some current, but it's a weaker amount of electrons lighting up that filament. So the light bulb is a little weaker. And what we see in this picture is an example of HCl, right here, HCl aqueous. As soon as it hits the water, it breaks into individual ions, and you see here's a chloride ion, here's a hydronium ion, hydronium. So they're in a 1-to-1 relationship, but you see 100% ions. So no neutral molecules. That is different from a weak acid like acetic acid. So when we have acetic acid, I'm going to write it like this, CH3COOH, and that COOH group is, let me write my AQ on there. So this is the acidic part. That hydrogen can come off because of that chemical environment. But these hydrogens on the carbon are not coming off. Okay. So we have the neutral molecule here, 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 here. And we only have the hydronium ion, or H plus CH3COO minus, and those are both aqueous. Right, this is our chemical equation. Let me add that arrow in. That acetic acid dissolves, some of it stays together as a neutral molecule, and some of it breaks apart into the ions. And here's what's interesting. It's about 10,000 neutral molecules for every one set of ions. So here's those ions. here, you know what I'll do is I'll make this pink. Right, here's the ion set. There's one hydronium and then there's one acetate ion in the picture. But there's more neutral molecules. And of course, I'm not going to draw 10,000 of these. But you kind of get the picture. A lot of neutral molecules in there. And that's why it's weak. It's just fewer ions form. So it's a weak electrolyte and a weak acid. It's an acid because the charged particle is hydrogen. So what does that mean? 10,000 neutral molecules for every one. Why do any electrons flow? I just want to bring us back to thinking about how many molecules might be in the solution. We might have Avogadro's number of molecules. We might have 6 times 10 to the 23rd molecules. So when we think about for every 10,000, one of them dissociates, it's still a lot of molecules, right? That's 10 to the 5 versus 10 to the 23rd. There's still a lot of ions that are able to pass the current. Okay, so that just sort of sets the context. That's really what we're thinking about. All those molecules in there, what extent of dissociation is there? All right, strong acids and bases. So we need to recognize acids. A lot of times I'll have the H in front, or if you're taking any kind of biology, I know STEM majors in chemistry don't always take biology. I certainly didn't take it till graduate school. But if you have that COOH group, that is commonly the way that acids look in our biochemistry, our weak acid groups. So we'll just memorize the strong acids. These are chlorine, bromine, and iodine when they are paired up with hydrogen, hydrochloric, hydrobromic, hydroiodic. And then those polyatomic ions, nitric, perchloric, and sulfuric. Notice that HF is a weak acid. It's kind of an exception because fluorine is that snowflake. Fluorine's like this extra special, doesn't share its electrons. Now, why that makes the acid weak, I don't quite get. Like, we can talk about electronegativity. I can explain the reasoning, but I just don't feel it. I just don't understand. Like, why? Why doesn't it? Why does it hold that electron? Okay, anyway, I don't know. So recognize those polyatomic ions, nitric, perchloric, and sulfuric acids. And for the strong bases, this is what I was talking about yesterday with that Tetris shape on the periodic table. So group 1 and 2. Okay, these are not quite to scale, but it's right here. You could color this in on your fill-in periodic table. I think somebody posted that, right? Okay, so lithium, sodium, potassium, cesium, strontium, barium, that little Tetris shape. Those are the cations. When you fill them up with hydroxides, those are the strong bases. And that's why, or it's correlated with, being active metals. Right? They react with water and they form these strong bases, and the base is caustic. Okay, so those are things that you just memorize. And it's helpful to know. I would maybe write it on your fill-in periodic table, so as you move forward in chemistry, you have your own beautiful cheat sheet. Okay, it doesn't have to be beautiful, but when it's written in your own handwriting, it's more memorable. All right, strong acids. Now, this is a technical term. I'm not just saying, oh, well, that's really strong. I'm saying strong acids. Strong has a very specific definition. And this is confusing because it's something that we use in our normal life. It's a word that seems familiar, but we're using it in a very technical way. Weak as well. I don't mean it's highly concentrated. There's a lot of stuff in there. It actually means 100% ionization. So if an acid is strong, it means a one-way arrow. It goes all the way. As soon as you put that HCl in water, it hits the water, and there's no neutral molecules left. It's all ions. So that's what it means to be strong. Now notice for sulfuric acid, it has 2 protons, but only the first one is strong. The second one, some of this stays together. So if we just put it in water, we'll get that 1 H plus completely by itself, but then we'll get that hydrogen sulfate ion staying together. The minute you put a base in there though, that base wants the proton, so it's going to grab that proton. Okay. Weak is different. Weak is a little bit different. Weak means that there are only some of it dissociates. Let me just clear all this. Let's start over. Only some of it dissociates. So we get this two-way arrow because if there's 10,000, remember I said, and this value holds for a bunch of these. HF is one of them. If there's 10,000 HF molecules, neutral molecules, hanging out together, surrounded by water, one of them for every 10,000 breaks into ions, into the hydronium ion and the fluoride ion surrounded by water. So there's a one of these and one of these. That means everything is present in solution at once. So we use that two-way arrow, and that means that everything shown in the reaction is there in the beaker at the same time. So that's what it means to be weak. Weak is less than 100% ions, dissociation into ions. And usually we have something like this 10,000 to 1 ratio. So we'll talk more about that in later quarters. Okay, so that's what it means to be weak. When we have a weak acid, we're going to write it as the neutral molecule as well as showing those ions, just to remember they're all present at once in those beakers. Okay. All right, so let's take a look at some of these. I feel like, just intuitively, that we're coming up on the end of a session. I'm ready to stop. So maybe I'll let you work ahead on some of those. This would be a good time to stop the video and fill in these beakers to complete this section. So you will need to identify strong or weak, so you'll look back at that list. If it's not on the list, then it's weak. If it's strong, we're going to write it completely dissociated as ions. If it's weak, we're going to write it as a neutral molecule and then a little bit of ions dissociating in there. Another thing we can do is practice our naming. So on each of these, go ahead and write the name above the beaker. Okay, so when you've done that, go ahead and click play again, and I will go ahead and fill these in. So draw my little water level. This first one is hydrobromic acid. That is on our list. It is strong. And so I'm going to write H plus, and those are aqueous, and Br minus. And if I wanted to be super accurate, I might write H3O plus, just to be super specific. That's what I mean. All right, what about the next one? This is, the nitrate is NO3, so this is the nitrite ion, and that's going to give us nitrous acid. All right, is it on the list? What's on the list? Okay, hydrobromic was strong. Nitrous acid is weak. It's not on the list. That was nitric. Nitric is strong. Nitrous is weak. So how do we draw that? We'll draw those weak acids together as the neutral molecule dissolved in water, and there is a small amount of ions that form. So I'm going to go ahead and write those in there too. All right, what's this one? HClO2. So HClO2 and HClO3 are the nitrate and nitrite. This is, sorry, chlorate and chlorite. So this is the chlorite ion, which means this will form chlorous acid. All right, our list probably includes perchloric and chloric, or maybe just perchloric, depends. Sometimes that one's a little bit in dispute. But let me circle, this one is weak. So again, we'll keep it together as a neutral molecule. And that's most of it, but there is a small amount that forms those ions, ClO2, 1 minus. Oh, and let's keep those O's capitalized. All right, what is this? ClO4. Oh, this is perchloric. Perchloric acid, and it is strong. So how do we write that one? We split it into ions completely. Next one is sulfuric acid. This is on the list, so this is a strong acid. And how do we write this acid in water? It's a strong acid. We are going to get that H+, and then only the first proton is strong. So we're going to keep the rest together, HSO4 with a 1 minus charge in water. So that's how they're going to stay in water. Oh, interesting, my color's changed. Okay, so strong and weak doesn't tell us about the safety. We could have a weak acid, such as hydrofluoric acid, is also very dangerous. It will soak into your skin and replace the calcium in your bones. And it's like a burn where the percent coverage of your body dictates how bad the injury is. So it's very toxic and dangerous. But it's only a weak acid. It only gives up some of those protons. So strong and weak doesn't talk about how much is in, how strong, that how concentrated the solution is, how much is in solution. It doesn't talk about how much is there. It talks about how does that molecule react? Does it go completely to ions, or does it just partially produce ions? Because even though HF is weak, it can still be very dangerous. Okay. So next we're going to talk about electrolytes. We're going to use, oh, look at that. My arrows didn't come out. We are going to apply this same thinking to ionic compounds and just classify these as a whole. This is tricky, right? This is a little bit harder. Wait, where did I leave us? There we go. So it's a little trickier, but go ahead and give it a shot, because that's so helpful when you see how all of these things work together and what's going to be in the beakers. This is building that chemical intuition. That's really helpful in looking at our reactions and understanding them more deeply. Okay, so I will see you on Tuesday or online in the meantime. And I am, yeah, have a great weekend. I'll stop rambling.